Okay, so this will not, cover any aspects of PostgreSQL. It's more on the aspect like how do we use PostgreSQL to enable, our business so that it grows even faster. The agenda of this talk is going to be something similar. I'll just give a brief intro about inMobi itself, what we do, so that you get to understand the scale of it, and then we'll talk about how we started and now where we are today. Now this is like almost like 4-5 years journey, which our database usage went through multiple phases, starting from 1 instance to 100+ instances today, and then we'll also talk about some of the challenges which we are facing as we talk today. Okay, so how many of you have seen ads on your mobile? Okay, how many of you liked it? Okay, so that kind of brings the fact that no one likes ads on your mobile, but that's what we do for business. So what we do is, we serve ads to mobiles every day, and we do around like 8 billion ads a day. Okay, and all this is being powered by PostgreSQL at the background. Okay, now if you don't like your ads, so what I would encourage is share more about yourself on the social media, so that we have a lot of data about what you want, why you want, and when do you want, so that we can make your ad look even more beautiful. Hope you might like it sometime in the future. Okay, so inMobi is a company which serves ads to mobile devices alone. It was founded in 2007, and it's one of the world's largest independent mobile advertising network today. So, Google's AdMob stays the first, followed by Facebook, followed by inMobi at the third, which we do around like 8 billion ads a day. And up to now, we have received $215 million funding. That's a huge money, where we are investing in all this technology and other things. And in order to ensure, we serve you the right ad at the right time, we analyze almost 240 terabyte of data every day, to figure out what you need. That's one thing which we are still working on it. And on a daily basis, we reach around 761 million unique users across the world with our ads. And we try to engage them. inMobi has been pretty well known in open source projects like Hadoop, Apache Hivestack, Falcon, and other things. One of my other goals this year is ensure I get PostgreSQL also into this list. So when we all started, like in 2007-ish, this is how our architecture. Is it visible from the back? So this was how our architecture looking like. We had a one PostgreSQL 8.3 server and one standby and one OLTP app and OLAP app. Everything was in this database. That was like the brain of everything. That's how we started it. And now, this is how it is, which is spread across like almost 6 data centers all over the world. And so this talk, what I'm going to do is, I'm going to walk you through what all the factors that triggered from this to this. That's all is, this is like, if you really look, this is like a movie. I'm going to show, this is the start, this is the climax. Now I'm going to walk you through the sequence, which helped me achieve that. Okay. Any questions up to now? If you have questions, you can feel free to stop me. And so the various factors, which kind of forced us to, iterate on our architecture day by day, these are the few things, One is, we just started as a proof of concept. Then we wanted to separate, as experts generally advise, right? We want to separate OLTP and OLAP databases. And then we had the initial success of our business when it just started. And then we want to expand it to new data centers. And then at some point, we reached, with one mission, we reached around like 45,000 queries per second, which we thought at this point we need to scale up vertically, which was not impossible. Then, we kind of moved to service-oriented architecture. And then there are quite a few operability issues in terms of, operating at this scale, and then as and when, we got the mobile adoption grew, we got more user base. Now we want to ensure, we are closer to users so that, we serve an ad in like less than 5 to 10 milliseconds. And then there's this, we also, took few learnings from our other teams, the application team, especially the applications which are stateless, and see, how we can try to incorporate those into the database itself so that the operations is a lot easier and more predictable and all those things. And then that's when we also, PostgreSQL 9.2 got released, where we thought, we'll get into cascading replication, and then Amazon Web Services, new products launch. So I'll walk you through all of these in detail, like how we started, what does this mean, why did we move, and all those things, and over the course of this talk. Okay, so this is how it was when we started. So you can just see, one database server. This is the master, this is a slave. This is the OLAP app, and this is the OLTP app. So everything was happening in here, like creation of a new ad, serving an ad, and showing the reports like how many ads were served, how many clicks, everything was happening here. And this served as also a processing node. So what I mean by processing node is the moment we serve an ad to mobile devices, all the mobile devices, we log it in a file, and then we store those into a table, and then we run our hourly aggregation. Like every hour, we'll say, okay, we served so many ads, we received so many clicks, all those processing was happening in this node. And this is how we started, and pretty much everything was working fine, because we just want to see whether it really works. And now what happened is, due to this, every hour, since we used to run the summary jobs, what will happen is the provisioning system, the OLTP system, we can see slowness. It like 50 minutes in an hour, it will work absolutely well, and then the last 10 to 15 minutes, it will like slow down. You'll get like random slowness and all those things. And that was a good sign for us, because it kind of validated that what we were doing was on the right path, because the business started improving. So then the first thing what we did is, we broke this PostgreSQL into two separate systems. We made it as a OLTP one and the OLAP one. So OLTP one was used just for provisioning, like creation of ad, creation of site, and all those things. The OLAP was just used for showing reports. So this one was really pretty painful. The reason is because initially when we started, right, all the tables, like your metadata tables, your dimensions and facts were sitting in the same machine. Now when we kind of split it out, right, what we generally people do is they create your OLTP table and replicate into the OLAP system, which might not be a real dimension table, which was optimized for OLTP. You just get it into your OLAP system and try to run queries. So we had exactly the same problem, where we have a table here which is optimized for OLTP, but it was copied into OLAP system, or your queries were joining, doing a lot of joins with these tables. So it was pretty painful to do this separation, and it involved a lot of application changes. And so once we got through this, then what we did is, now for all the metadata tables which are in the OLTP systems, like your site details, ad details, budget details, everything, we used to take an hourly dump and restore it here. So that's how stupid it was when we started. So quite a few challenges with this. What happens is, we had a cron which wakes up every hour, takes a dump, restores it. And many a times the cron won't work as it was supposed to. And then what will happen is, whenever you do releases, especially when you add more rows or columns, people will add it over here and forget it here. So what will happen is, your dump will start and it will fail over here. So this was continuing for a while. And then parallelly, what happened is, since we do serve ads from all the front end boxes, we started serving more ads. So that means we need more processing power here, right, especially in the app layer. So then we added more app machines. Now with more app machines, I cannot have a cron which is running from here and moving data around here. And that's when we introduced Sloney into the scheme. So with Sloney, that kind of solved us the schema problem, so that you follow the execute syntax, so that when you add a new column or something, you do it via execute command, so that Sloney will execute it in all the available nodes. And then up to now, since we all started up, right, the one classic case was the username password of database, right? It was like open to everyone in the company, right? So anyone on a given day would just log in and do something, because at startups, generally what you do is you work on trust basis, right? Because when you're starting, you want everyone to be more efficient. So the username password was shared across. Now we kind of cut it off because with Sloney, when people you just go ahead and add a new column without doing an execute, then what will happen is the column will be only there in the master. On your slaves, it will not be there. Quite natural. So then we kind of put in a, a database release policy where we ask people to go via GitHub. That is something which it really worked for us. So what we do is we get the schema into a GitHub. That's how we do version controlling of database schema. And then whenever people want to make any changes, we ask them to send a pull request with their changes. Then someone from the DBA team would review it, renew it, and then push it to production. So this is how we change the release policy itself. Now with this, we also got a lot of flexibility. Like if I'm pushing a certain version of an application, right? It also had the schema changes along with that. It gave us that flexibility. And for the database schema itself, we also had a log of what all changes were merged into the production schema. And you can always go visit it, revisit it, whatever purpose you wanted. Plus, it also enabled us to do a lot of automation around creating your QA or development boxes. Say for example, if I'm running a quick sanity check, I just want the latest schema alone. Earlier what we used to do is every time you go to the the production box, do a PG dump, get the schema out, restore it, and do it. With this, we got it so that people can go check it out from GitHub and then run those changes. They will get the latest schema which is available in the production. So it was working pretty well for quite some time with this setup. It was like almost 6 servers. It was pretty good, and we never had any complaints as such. And then that's when initially this business was started in APAC, and now we wanted to venture into the US market. And now since this is a mobile advertising business, I can't serve an ad sitting from Singapore or Hong Kong to someone in US because the native latency itself will be somewhere around 60 milliseconds, right? Even just the ping latency. So now that means it makes sense for us to have a new data center in US so that when I serve from US, I can serve an ad for even less than 10 milliseconds. So we kind of got a new data center in US. Now the next challenge is all the data which were here, right? All my OLTP, like what all the ads, sites, everything which was created, it was sitting in one data center. Now I need to replicate those to US data center because when my application serves anything, I need to know which ad to serve on which sites and all those metadata. So we kind of used Sloney for this when we started. So we were using Sloney for WAN replication. That was the first time we got it, and even the moment we told, okay, we are doing Sloney for WAN, and I'm going to open my port 5432 across data centers. Another security team come back and told, oh, you're opening a database port outside of the data center to the world? No, this is not working out. So that's when they drew out a blank. Then actually we went out with something called as S-tunnel. So what we did is we implemented a S-tunnel, and then S-tunnel via local port forwarding on a local machine, which S-tunnel took it to the remote box, and that's how we got around this. And this, the moment we got this setup, yes, probably the business problem was solved where now my ads were being served like less than 10 milliseconds, and we really partied harder because US was more mature market in terms of mobile advertising. So we thought, we'll expand a lot more. But, the business problem was solved, but the technology problem remained a lot with us. Because the moment you get into WAN replication, what happens is S-tunnel, all of a sudden, due to your network instability, it breaks. I can see a lot of idle in transactions at both the ends where this transaction is trying to do something, the connection is broken. Or let's say, I have a network outage for 2 hours, and now my network is restored. Now, the moment it's restored, what I want is I want all my data to be replicated immediately, right? That's quite natural to expect. But the problem with Sloney is, even though you give like huge bandwidth, it cannot pump beyond a limit. Because every time, those SL log 1, SL log tables, you fetch like 100 or 500 rows max group, and then it sends it in chunk. So even if I have a huge bandwidth, it was not able to utilize it. So there are like quite a few operational challenges like this, which we are running out with. And the other biggest problem is usually, whenever this idle in transactions happens, so in Sloanie what happens is you have this SL log 1 and SL log 2 tables, which capture all your changes and then forwards it. Now, for some reason, if one of the transaction is stuck, the log table rotation will not happen. So that means your SL log 1 or one of the tables will keep on be growing, and at some point it will slow down the entire system. In those cases, generally what we do is we throw out everything, recreate the Sloanie clusters from scratch. This was part and parcel of the operational life with this architecture. And the other challenge as part of this itself, since we started growing, we had like a database where we really didn't have anything like service-oriented kind of stuff, where a table, if there are like 10 different applications, all 10 different applications would be reading and writing into a table. Okay, so now it introduced even more challenges, because when I am dropping a new column, I need to coordinate with all the teams out there saying, okay, I'm dropping this column. Is your application impacted? Please let us know. So it involved a lot of coordination with various teams within the company. And this kind of was slowing us down drastically, because it's like if you're coordinating across 10 teams, you need sign off from 10 different teams, and then they'll say, okay, no, my development cycle is not now, I'll fix it in next month. So you had all kind of hustles along with this. So that's when, we decided we'll move to a service-oriented architecture. So what we did is, so you had this monolithic database which had like roughly 600 tables. Those 600 tables contain the entire logic around it. So now we kind of took an approach where, based on the functionality, we broke those 600 tables into like 30, 30, 30. So that based on this functionality, okay, this is what the tables are needed. So we kind of broke into small databases, and then created it separately. So now what does this mean is, it kind of solved the other problem. Like now what I can do is, for applications which are dependent on other services, I can ask them to use the services generally instead of reading directly from the table. But this introduced a penalty for us on the Sloanie nodes, because now that means I'll have more master databases. Earlier I just had only one, but now due to this architecture, I'll have like around 20, 30 masters. Now there are still, few things which were being cross-replicated due to various reasons. But this actually, it helped us to reduce coordination among multiple teams. So that if I'm doing any changes in my database, it was like I was almost exposing an interface at the API level. So if I'm doing any changes, as long as my interface remains the same, I don't care really what columns you add or what columns you remove, what new tables you add, and all those things. So this, reduced the release coordination drastically. And then we also tried, various things so that, we can kind of run Sloanie reliably over WAN. So few things which we tried is, we tried QoS, like saying, okay, for this port from this machine to this machine, we'll allocate certain bandwidth. We tried that. Even it kind of helped us, but it really didn't go a long way. And then the other things which we tried is, we also tried to get, a leased line, between our data centers, so that I won't have any network instability or packet losses and all those things. So we kind of tried various approach, but the operational challenges were still continuing, where I used to create a cluster, drop a cluster. That was like an everyday norm. And then now, since our business even picked up further, now let's say we want to venture into Europe, right? Now if I want to venture into Europe, it's straightforward. I can't serve it out from US or Hong Kong or Singapore, because my latency will be higher. So we got a new data center in Europe. So now it even added more nodes into our Sloanie, right? Which was causing even more troubles, but we were still living along. And then at this point, we are also looking at, okay, now there are the stateless apps generally, right? How do they manage? For them, let's say a mission coming or going down really doesn't matter, because at the end, for them, everything still works, because they have a cluster of missions doing the job for them. So we kind of got influenced by that, and what we did is we introduced this layer, a load balancer, a Citrix load balancer or a Netric, NetScaler, load balancer. We introduced this and we created a virtual IPs there. And then what we did is for all our apps, if you look at earlier, my app will be talking to the DB directly here. So that means if, let's say this machine goes down, I need to then go ask my application team, hey, this machine is down. Can you remove it from traffic? Instead of reading it from here, read it from here. So this also involved a lot of coordination with various teams at 2 a.m., 3 a.m., which was really, really painful. So then what we did is we introduced this layer, and then we gave this virtual IP to the application teams. Now, what happens is application team will always be talking to us via this load balancer, and this load balancer will be redirecting the traffic to the all slaves. So this kind of solved the problem of a machine going down or anything of that. The application will still work as long as we can serve their queries in a faster manner. So, and since we never up to earlier, we never had PG bouncer as well, because the connections were also limited and all those things. Now the moment we went in this mode, application team, what they did is they kind of scaled up without even informing us. Right? They keep on adding more servers. We will be like, oh my God, what happened? My WIP is down, or my database machines cannot handle load. So the first problem which we identified was they were establishing too many connections and leaving it idle. So then what it did is in each of the database boxes, we also got a PG bouncer layer so that we were doing the connection pooling ourselves. So this gave us a lot of room for us to grow. And this is how it stands today, especially this bit, right? The app to load balancer to DB, this kind of served as a blueprint for read scalability for us. So tomorrow, if I want to add like hundreds of slaves, I just go set up Slowney, or SR will look into it. I can set up Slowney, one more, add it to the load balancer, and the application will start sending traffic to it. And now if I want to take a machine for maintenance, right, I just go bring the PG bouncer down, take it out, do my maintenance, put it back in traffic. So all these things, if you really look, the control was within the DB team itself. We had our own freedom to do whatever we want as long as the virtual IP is taking traffic and serving queries. So this gave us a lot of freedom and solved a lot of on-call issues. And at the same time, at this scale, we were almost doing around like 4 billion ads a day. So the scale hit beyond the limit where we can run our monthly aggregation queries in DBs itself. Because when I mean 4 billion ads a day, that means 4 billion rows, 4 billion rows in a table. We did with partitioning, and then we tried to run hourly aggregation and all those things. But at some point, we cannot do it on a single machine. Even if I were to do it like vertically scaling, we even spent like around 30,000 USD with a 256 GB RAM box and a SAN with SSDs, all those things. But even then, we cannot compute those hourly jobs in the database itself in one machine. At this time, we didn't really look at where I can run my hourly aggregation across multiple machines. So we are still stuck with the limitation of one machine. So then we kind of started moving this processing into Hadoop, where the hourly summaries used to run in Hadoop. Okay, so this served us for pretty long, and though we still had issues with WAN replication, it still kind of continued, and we also expanded to 3 data centers in the same time for more traffic. So at some point, I had roughly around 16 slaves in Slowney, which was really massive for us. Anytime we do releases, there are a lot of operational errors. Like people would forget to add one node, or whenever we add new table or new sets, it was kind of painful actually. And the other factor here was all the app, when it talks to DB, they don't issue queries. We usually run via stored procs. So from app, they call the stored procs. So this also introduced one more challenge. What happens is when you're pushing a new stored proc, when you have like 60 odd machines, people forget to put in one of these. So now application, they will come back and say, okay, hey, my stored proc randomly works fine. Right? It was a painful thing to debug, and also it was tough to enforce on people, okay, ensure release, make sure this releases on all nodes. It was, we also had a lot of automations around, but nothing really solved us. And the other bigger challenge is now when I am adding a new column to a table which is being heavily utilized. Imagine I run an execute command and that alter table statement needs to run on 60 machines which are spread across data centers. And we really don't know what is happening in which mission or what kind of reads is happening and all those things. So that was even painful. So the release process was, it even used to run for like 4 hours when you want to do make any changes. It was drastically slowing down the team, and the team was feeling really inefficient. Well, I'm just watching something, waiting for when it will happen, rather than saying it will happen at this point in time. So exactly at that point, we got PostgreSQL 9.2 got released, and this was really a welcome change for us. So what we did is we just cut this layer. Instead of Slowney, we just moved it to streaming replication just for WAN alone. So internally, we still have Slowney within the LAN. And by the way, Slowney within the LAN, it just works awesomely without any issues. You just set it up, leave it running, it just runs until you go and muck around with it. So then we moved it from Slowney to SR. This kind of solved a lot of problem for us. Now, even earlier here, what would happen is, let's say if one data center cuts off. Now, if I want to hook my one data center into another data center, it was a lot of changes in Slowney where I need to do a move set, failover, this, that. It was not really straightforward. Now, with SR, what we did is we had like 4 data centers. So you had your master and 4 spread out, fan out. Now, even if one data center goes down, I can hook the other data center into the other data center, because I just go change in the conf file, in the recovery.conf, say, okay, instead of connecting to this, connect to this. This is your new master. So it kind of works seamlessly. And the other thing which it solved us was, now since this is SR, whatever changes I do here, right? We had a hop machine here. Whatever changes I do here, let's say I push a new stored proc or I push a new schema, it kind of automatically replicates, because anyway it works on wall logs and streaming replication. So it was pretty straightforward for us from this perspective as well. And maintenance deployment was like, I just push it out and forget about it. And the one thing which we also did as part of this is, so app and DB deployment always need to be in sync, right? So I first push my DB and then I push my app so that the stored proc name, what I give, should be matched or should be already be existing and all those things. Now, at this point, what we did is we also introduced versioning to our stored procedures. So the moment we introduce versioning, what happens is the moment it's ready for a release, DB team would separately go and push the changes. Everything has a version tied to it, like V21, V22, or V product A, product B, and all those things. So we kind of pushed it, and everything had a new name to it. So now, with this, the DB team would separately go ahead and push the releases, and the app team, whenever they wanted to read those stored procs, right, they just give whichever version the code is compatible with, and then they moved on from there. So this also kind of reduced the friction. And when we did this, one interesting thing happened is, what happened is, let's say, for some reason, one of the data center went out. Like it got delayed for like say 5 hours, 6 hours, it completely broke out, right? That's when we realized it broke out only for replication. For app, it was just working fine for them because it's end of the day app was internet connectivity was there, so they were serving ads. Now, during these cases, what happened is the database didn't have the stored proc which the app was using. Because though the changes were done here, due to delay, it didn't replicate, and the apps were all failing out. So this is when what we did is we introduced one more aspect here. So you remember we had this PostgreSQL and PG bouncer. And then you have a load balancer which will run a health check and to say whether the latest version is in traffic. So we kind of modified the health check itself, so that instead of giving it a wrong data, we will automatically bring the DC itself down. Even application would not serve any traffic. Application also will fall over to other data centers. Any questions here? That's all like all over the places. It was part of the stored proc name. Oh, okay. The name, the stored proc name would have version and the product. Okay, so with quite a few automation around here, so even if my entire replication is delayed for 4 hours, what we'll do is we'll kick the entire DC out of traffic, and similarly the application will also do similar. If you want, it will kick entire thing out of traffic, and this is how it has been working, and this is pretty smoothly working with zero operational issues up to now. As long as even if my network goes out, I just don't really care about it, because the moment it's restored, it will automatically catch up. And the best part in comparison with Slooney was not able to utilize the entire bandwidth if I allocate to it. Let's say I allocate like some 200 Mbit. Slooney was not capable of, at least in our experiments, it was not capable of exceeding beyond 50 Mbit. Now with this, TCP IP stack was the limit. We have seen it going up to almost 180 Mbit per second. So the moment you give a huge bandwidth, my replication delay would automatically come down, because now you have huge bandwidth to pump a lot more data. And then we also had an interesting business requirement where they want a delayed replication. So this delayed replication is not like a 24-hour delay. So what I want is, I want my database state as of 2 p.m. yesterday. So that means at any point in time, it is not a 24-hour constant delay, it's like day. I want to see the database what it was like yesterday 2 p.m. for this entire day. So which was, I think as of 9.2, this support was not there natively as well. It had support for delayed replication in terms of constant 24 hours. So that means or any amount of time, where let's say if you give it as 1 hour, my replication will be delayed by an hour. But what I wanted is, I wanted it to be snapshot at, let's say, 2 o'clock. For the next 24 hours, I want the database to be exactly at the changes what all happened at 2 p.m. alone, and not beyond it. The moment next day comes in, I want it to go to the next day 2 p.m. So we kind of had this weird requirement. So what we did is, we kind of archived the wall logs, and we looked at the wall log timestamp, and then kind of replayed it. And then I know it was a little bit hacky, but it was solving the requirement for us. The challenge there is the wall log timestamp might not be accurate, because when a new file was created, it would have been there. But it kind of worked for us, and then we also got, we'll replay a log file and then get it out. Okay, check the last recovery timestamp. Okay, again do it. So we are kind of doing a lot of trial and error to get this out. And the other challenge which we also had as part of this setup is, earlier with Slooney, I never had any issues. I fire a query, it will execute it at any cost. My query will never be cancelled. Now with streaming replication, if my query was running for more than half an hour or 1 hour for whatsoever reasons, the queries would be cancelled. Now what we did is, to ensure it doesn't cancel much, then we did a vacuum defer. So that we are saying, okay, don't clean up the rows which this is reading, and we also enable a hot standby feedback. We kind of tried all those things approach. It all adds to, pros and cons. I solved this problem, but I increased my bloat. I reduced the bloat. Now so this was kind of continuing like this. And to a greater extent, we don't have all these issues now, because we also introduced one more caching layer and all those things. So it kind of working pretty well for us with this. And now, so this is all what we did in our data centers. Now, Amazon Web Services, there's a new thing which got launched, and everyone wanted to use it. And we had around 4 data centers. Now let's say if I want to do someone in Tokyo, right, Japan, or let's say something in, the Sao Paulo in Brazil, right? We really don't wanted to invest more in data centers because the cost was, running into millions of dollars. So which we thought, okay, it's not going to really help us because the traffic from these countries are also less. So we are doubtful whether will we get the ROI what we are investing in. So that's when we thought, okay, let's move on to AWS because they had their data centers in Sao Paulo, Tokyo, and Singapore. So what we did is we took the exact same setup, ported it to AWS. So instead of machines, hardware, we had your EC2 EBS volumes. Instead of load balancer, we had an elastic load balancer. So it was seamless, straightforward. Just go create instances, set up replication, put it in an ELB. ELB will start distributing traffic around it. And with this, we also, kind of achieved like, a kind of automatic scalability for reads. So we had a lot of scripts around here. What we do is we generally monitor, okay, how many hits am I getting at ELB? We know each machine can do like some 4,000 queries per second. So we kind of monitor how much hits I'm getting at my ELB. So the moment I watch it, the moment I see it hitting a limit, then what we do is we automatically start a new script which already had a pre-baked AMI with Postgres installed on it. And we also do daily snapshots of the data directory. So we took that AMI, took the snapshot, attached it, put it in replication. So with this, my streaming replication setup was almost, I can get my streaming up and running within a matter of 10 to 15 minutes. So if I want to add more scale, matter of 10, 15 minutes, run a script, it will automatically get a AMI, get the latest snapshot, attach itself to ELB, and add itself, start taking traffic. So with this, as and when we get more business, I don't really need to worry about particular AWS region at all. They can keep on adding more traffic, we'll keep on expanding. So we kind of, though we had a lot of quirks around it, like how to get it reliably working, but the moment we got it working, it kind of gave us automatic scale for database reads, which generally we look at only applications, right? The stateless applications which will scale automatically as and when you add more nodes. Similarly, what we did is we did the same thing for database reads. And all this thing which we are talking about, it works only for reads because writes is something which is stateful and you can't apply all these techniques to stateful writes or applications. And so currently, these are the two setups which is still running. So if we go back where we started, so this is how we started. Now this is our entire setup is today. Any questions? Okay, so that's all what we have did in the past. And now, what are the few challenges which we are having as we start with, right? Now, the biggest challenge here is today, as and when we are facing is, now this particular thing, from one data center to other data center, we transfer around 800 WAL files per hour, which is like really, really huge. Every hour, we generate around 800 WAL files. That is the volume which we are talking about. Because this machine, what it does is, it assembles a lot of data from multiple masters, somewhere around 30 odd masters, where selected tables. So it kind of gets from all those things, puts it here. So which, we are trying various things to reduce this count. I mean, the other major factor is, which I was talking about, we also do that vacuum defer cleanup. So now if I do that, what happens is, the moment you update that, you'll have a lot of blot. So that when the entire page gets written during checkpoints, it will bloat up. So this is something which we are still dealing with. So we are also trying, some other external compression solutions over this link. Instead of doing at the database level itself, I'm doing something which is external, compress the WAL file, send it out. So which, we are still figuring out how to solve this particular problem.
Question. So do you just let the vacuum run at any time, or do you schedule that?
We have a heavily tuned auto vacuum at the table levels. So we never switch off, or we never have a auto vacuum daemon outside. It's all, the regular auto vacuum process with, I think we have around like six process. And we also know the application to a greater extent, so we tune it based on the table wise as well. We set those scale factor, everything at the table wise.
So does it run autovac, or
Yeah. It has been working pretty successful for us.
do you schedule that?
No.
No?
It's the auto vacuum which comes as part of the default Postgres. Except that we increase the number of process alone because it was not able to keep up.
Do you see any slowdown since the autovac's on?
I mean, there are slowdowns, but nothing really noticeable for our loads up to now. Because, see,
You have not a lot of inserts, or
we do have, our workload is like 40-60. 40% write workload, 60% read workloads. And see, at some point, if I go back, exactly, at this point, right, we had only one master. The moment we got into the service-oriented architecture, at this point, we were roughly doing around like 45,000 queries per second. That time, yes, we had a lot of issues. Auto vacuum not able to catch up, table bloating up. Every time a table bloats up, what we do is we shut down application, create a new table, flip it. We are doing all this. It was heavy operationally as well. But now the moments we got into this model, where we have a service-oriented architecture, it kind of, we don't see much. Now, if you really look all these masters which I'm talking about, it will be doing something in the order of 10 to 15,000 queries per second. It's mostly on that order. So wall file is one challenge for us which we are now facing. And the other thing is write scalability for individual masters. Now, with service-oriented architecture, yes, it kind of solved us a problem, but now we are hitting a stage where the ads which are created in our system is like, running into some 500K ads per day. And now that ad I need to replicate all across, and the provisioning system itself is started, slowing down, and where I kind of need to figure out how do I do write scalability across multiple data centers, where customers in Europe will hit the Europe data center to create an ad, US will hit US, Singapore will hit Singapore. That is something which we are yet to solve. And the other thing is FDW for reliable data movement. As I was explaining in one of my earlier slides, the reporting aspect, the computation of this report, we moved it into the Hadoop system. Now from Hadoop, we get this summarized data which we need to insert into DB. So that we first tried, okay, we do a rsync, copy, insert. Even that every hour we used to get somewhere around, like 35 GB of process data which we need to load. Then customers can look at it and all those things. So we kind of, investigating on FDW, can I use it to transfer this volume of data across DCs every hour? That is something which we are still figuring it out. And the other challenge which we are having is our data warehouse, as it stands today, is somewhere in the order of 14 terabyte. And this is sitting on a single machine. This is just the process data. Now with this, if I run any query, it kind of works because we have a lot of aggregation on top, like something similar to a materialized views. We have created materialized views so that when you want to look at any report, you just run one query instead of doing join and aggregation on the fly. But that has its own challenges. But the point here is, even it is not scaling in terms of disk space or in terms of computing. We need something which can really work across multiple missions where I can get like horizontal scalability. And Amazon Redshift is one thing which we are evaluating for this. And I'm not sure how many are aware, there is this InfoBright which also recently released their enterprise edition which works on Postgres. InfoBright works on a different model, and that is one more thing which we are evaluating, which offers both compression and horizontal scalability. So that tomorrow I add more nodes, I should see a similar, improvement in my queries. And The other bigger pain is incremental backups. If I want to do backup of my reporting database, which is 14 terabyte in size, I literally can't do anything today. So what we do is we generally keep those data in the Hadoop itself, so that in case if it crashes, we kind of get it, insert it, and redo all these things. So incremental backup is something which is a big pain for us, and we're just still trying to figure out. And there are other few minor quirks, like major version upgrades. So when we did an upgrade from 8.3 to 9.2, we almost took a downtime of a day to upgrade all our systems. I mean, though we had Slowney, it works across multiple versions, but there are a lot of quirks around it. It took almost a day to upgrade our entire infrastructure. So, I mean, if I go back to my management and say, okay, I'm upgrading my database version, a strict no, because no longer they can afford that kind of downtime. Probably we did it when it was small, but not anymore. And the other interesting thing which I was just going over is, with replication itself, with streaming replication, right? It's like I replicate everything or nothing. It's straightforward. Now, for our business needs, where there are few critical tables which deals with budget, what we wanted is, I really don't care about my other tables, whether they replicate immediately or not, because I can live with eventual consistency in those cases. But especially for my budget tables, I cannot live with that. So, we are also thinking out, how do I say, okay, these are few priority tables, replicate them immediately. These are non-priority tables, replicate it at your own time. Because with priority tables, I have a lot of money riding on it. With non-priority tables, okay, I can take a hit. So that is yet another challenge which you are facing. And that's it. That marks the end. Have any questions?
What OS?
We run it on CentOS and Ubuntu.
How often are you doing checkpoints? Or how often are they occurring?
On a master databases, we roughly do around like 15 minutes, or usually it gets triggered by the number of wall files itself.
And how often does that happen?
Wall files, if I remember correctly, we have around xlog. It would be around like every 4 minutes or so. I mean, because the wall gets filled up pretty fast.
You realize that the more time you have between checkpoints, the less wall that gets generated.
Yes, we did try that for this 800 thing, because at the moment you do a checkpoint, the next immediate write will write the entire full page.
Okay, just wanted to make sure you were aware.
Yeah, we tried it. So, I mean, this number is like on an average. We hit it, it hit up to 1,200. Then we did checkpoint reduction. Then we removed a lot of tables from replication. There are like few reporting tables, we removed it. And the other thing which we did is, since we don't want the queries to be cancelled, right, in streaming replication, we kind of went back, okay, let's not do vacuum differ, because the moment it is vacuum, my table is going to be bigger. That means my rows are going to be sparse, it's going to be spread across, which will increase my traffic. We tried all this. After all our experiments, we are at 800. But, I mean, it's still a challenge, but not that big of a really.
But if you can increase checkpoint segments, you'll generate fewer wall files.
Yeah, I mean, I can still try more, actually. Yeah, that's a good line. So we also have a dedicated line, so it's kind of, I mean, it's not a bigger problem, but yes, the moment, this is something, which is like a time bomb which just keep on ticking. The moment this hits beyond, like, if I hit it like 2,000 every hour, I'm sure I'm going to give up. I need to figure out some other alternative mechanisms. So it's still in the manageable state, this one. Any questions? From? So we generate the CSVs and then copy it across. Yep.
You said you were all running off stored procedures. Did you guys look at using PO proxy instead of the hardware load balancer that you're using?
Sorry, come again?
Have you looked at using PO proxy for your load balancer?
No, not PL proxy. We never tried it because I thought PL proxy was more on the write scalability end, which we need to evaluate. For read scalability, hardware load balancer was serving us pretty well. Oh, is it? We never tried it out, PL proxy. Okay, thank you.